truncate it in order to invert. Okay, when we truncate it, we'll go with m running from 1 to n. And you can either work with an infinite dimensional matrix system or an n by n matrix system. Of course, if you have an n by n matrix system, you learn a lot of things in school on how to invert them. You learn about linear algebra, you learn about MATLAB, you learn about Cramer's rule, you learn about Gaussian elimination, and so on. Okay, so this world is replete with knowledge on how to solve this kind of system when it's n by n. And usually we don't have to remember those methods even. We just go to MATLAB and just call, okay, A inverse, and find its inverse, okay? But then, if it's infinite system over here, and if you want to solve this equation in its original form without truncation, what choice do you have? You don't have many choices. One way to solve this equation is to solve it iteratively, by iteration. Okay, let's discuss an iterative method. Iterative methods are very important to solve linear algebraic equation in the modern world. Okay, let's assume that it's infinite by infinite, and that I do not want to truncate my matrix system. How do I solve this matrix system? I can divide my matrix A into, say, a diagonally dominant part, which represents the diagonal term of A, plus the off-diagonal part. Let's assume that this is, in many physics problems, diagonally dominant. So in a sense, D would be larger than T. T is the off-diagonal term. And this is the diagonal term. Okay, I can always break a matrix system into such. And then if I do that, then this matrix equation that I have here can be written as D dot F. I just take T to the right-hand side is equal to G minus T dot F. F is the unknown. In the iterative method, you will make a guess for the unknown, and you will solve this equation iteratively. Okay, if you make a guess for the unknown, you just plug in that guess and then find the next iteration in this manner. Okay, so this is called an iterative equation. You might start with f of 0 is equal to 0, nothing. And then you just get f of 1 is equal to D inverse dot G. Okay? D inverse is easy to find because it's diagonal. You can invert it quite easily for all the elements from 0 to infinity if you want to. And then you can find f of 1 from 0 to infinity as long as you want in as much memory you can get in your computer. You can store this vector f of 1 as long as the vector that you want to form. Okay, and then you plug it in on the right hand side and then iterate and iterate and iterate until you get convergence. So this is a simple iterative method. And there are more sophisticated methods around in the world. And mathematicians have actually spent a lot of time working on very many different kinds of iterative methods to solve matrix systems, which are CG, bi-CG, CG square or CG stabilized, GM brass, and all these are alphabet soup for solving the matrix system iteratively. And in theory, you can deal with the infinite dimensional system if you want to. Okay, you just have to truncate your summation series. Okay, so this is Just an example of what you would do when you're in contact with the real world. And then in general, an operator, I would like to talk next about bilinear expansion. Bilinear expansions are expansions that look like this. If I have an operator A hat, I can invert a identity operator in front and behind it. I can use this identity operator. And if I do so, I would get an expansion that looks something like this. And M and A like M. I use a different index M for the two different identity operators. And this is called a bilinear expansion because if I call this matrix element A and M, it is of the form of N M psi N A N M psi N. In other words, you expand an operator in terms of two autonomous sets. And these vectors are the transpose of each other. And because they're transpose of each other, this outer product will still make this behave like an operator. Okay? So each of these terms still behaves like an operator because the outer product between two vectors similar to this one over here. Each of these behaves like an operator because they form outer products. Okay, another concept that is very important in quantum mechanics is actually the trace of an operator. And we do that over and over again in quantum mechanics. And we know what the trace of a matrix operator is. And we say that if I have a matrix M, its trace is just the sum of its diagonal elements. That is what the definition of a trace is. And it turns out that the trace of an operator is independent of what representation it has. This is called a matrix representation of an operator. Okay? And depending on what basis functions you use, this is called a basis function. Okay. Depending on what basis functions that you use that are complete and orthonormal, you will get a different matrix representation. So if you want to find the trace of an operator, the first thing you do is actually to find its matrix representation. Okay, and then the trace is just given by AMM. M is to the 1 to infinity. It could be something like this. Okay, trace of an operator can be defined to be like this. And then it will be just sum of M is to the 1 to infinity psi M A hat psi M. And this process is independent of what basis functions you use as long as they're complete and orthonormal. Okay? And I'm going to show that this is also the same as if you were to switch to a different orthonormal set. You're going to get the same trace. And let me prove to you this fact. Okay? Let me prove to you this fact. So, if I have a different orthonormal set, I can always form identity operator in this manner. If I have a second set of basis functions that are complete and orthonormal, I can always form a new identity operator in this manner. Okay? So, if I do that, then I can insert this identity operator somewhere in here. And let me call this n in order not to confuse the indexing. Okay, let me just insert the identity operator in there. And then they can, of course, exchange the order of the summations because some of those are not dependent on m and n. Okay. So I will have size of n over here, size of n over here, and then I will have a at size of m. Okay. Now I exchange, these are scalar numbers. Remember, these are just inner product, so they're scalar numbers. I can bring this out front over there and write this as mn size of n, a hat size of m, size of m, size of n. Okay. Now I take this piece. What is that piece over there? If I take this piece as sum, this is the identity operator, right? That piece is the identity operator, so I can remove it and convert it back to. So voila, you see that the trace of an operator is independent of the basis that you choose. Okay. So oftentimes we just write a trace in this manner without specifying the basis that we choose to calculate it. It doesn't matter, you can choose any complete and orthonormal basis, then you can find this trace. It should be the same. Okay. And you can also show that if you choose those bases to be the eigenvector of, A, so if you choose size of m to be the eigenfunction of A, then this A times size of m becomes just a scalar number times size of m, and you can replace them then with size of m, size of m. Okay. If we have the property that this is true, you choose those to be an eigenvector of the operator A hat. And if you substitute that in there, you get that thing. And from this, you gather that this is 1, because these are orthonormal bases. So the trace of A is also equal to the sum of its eigenvalues. Okay. So if you know the eigenvalues of the matrix A, or the operator A, the trace is just the sum of its eigenvalues. And then one thing we proved before was that trace of the matrix A times the matrix B is the same as trace of the matrix B times the matrix A. Okay, we proved that in class a few lectures ago. You can go back and look at chapter 1, I think, or chapter 3, or some of the chapters that we did before. Because of that, it's also quite easy to prove that this is true in general for operators. Okay. So if you were to transpose the two operators and take their traces, then they have the same trace. Okay. So traces are important in quantum mechanics because we are an alternative to finding the expectation value of an operator. In quantum mechanics, we say that a wave function size of m, x in one dimension, or a size of m, r, is used to represent the state of the quantum system. Okay, if the electron has this wave function, we say that the quantum system is having the electron in this state. These are also called state vectors, because they represent the state of the electron. And remember before that we called that in classical mechanics, in order to understand or know the state of an electron, you have to know its position plus its velocity. Then classical mechanics says that you can use that to compute where the electron should be in the next moment and so on. So in quantum mechanics, we say that in order to know the state of an electron, you have to know its state function or the wave function that is associated with that electron. Okay? So there's something called the expectation value. Of an operator. A hat. And that is defined in quantum mechanics to be, this is usually used with this notation to be the state of the system, the state of a wave function that describes the system times this times that. Okay, this is usually defined as that. And a corresponding linear algebraic notation would be that this is analogous to having a vector U that defines the states of a system times a matrix A times another vector U. Okay. Remember that we say that this is like a vector, this is like a transpose of a vector, this is like a matrix operator. So its linear algebraic analogy would be this thing over here. So given a matrix operator, if you have a state vector, like what you would do in control theory, if you have a state vector and you like to find the expectation value of that matrix operator at its present state, you calculate this value. And we'll go into the physical interpretation of what this means in a little while. But I just want to relate this notion to the trace of an operator at this moment. And it turns out that you can write this in terms of the trace of an operator. Okay, let's see how we do that. I can write this in linear algebraic notation first. And then if I write it down explicitly, this inner product will look something like this. Okay. And then I would transpose this. I will put this at the end over here and write this as AMN, UN, UM. Okay? And I will put a conjugate over here. Now what do you recognize this product as? That product at the end there. It is? If I were to multiply two vectors. That's what? Yes, very good. It's an outer product, right? An outer product in index notation. Okay, it's an outer product because it will produce a number that is dependent on both n and m. So that number must be a matrix. Okay, so that is an outer product that we have over here. So you can think of this as a matrix. So this is like M, A, M, N, B, N, N kind of thing. Okay, this is a M, N times B, M, N. And what do you recognize this as? Sum of N, M, A, M, N, B, and M. So this gives you a matrix C, but then you make the first index and the last index the same. That is just the diagonal element of the matrix C, right? So if you write this in this manner, if you sum over n first, and this actually gives you CMN, CMN, so this is like the trace of C. Okay, that is like a trace of C. But what you notice then that is just that if I were to take this explicitly, it just says that this inner product used to find expectation value of is the same as taking the trace of this matrix times that matrix. Okay, trace of that matrix times U transpose. And this is what I call my matrix C. Okay, that expectation value calculation that occurs over and over again in quantum mechanics. We haven't given you its physical meaning yet. But that expectation value can be calculated using the formula on the right-hand side instead of the formula on the left-hand side. Okay, this is a matrix which is called a density matrix. Okay, so this is also written in the form that if you know the density matrix of a system, if you multiply by the operator and take this trace, you find the expectation value of the operator. Okay, the density matrix is a very important concept in quantum mechanics. It is calculated by taking the vector and multiply by its conjugate transpose. The good thing about the density matrix is that it's an alternative way to define the state of a system. We can define the state of a system with a state vector size of m. Okay. We can also define the state of the vector by the outer product between the two vectors forming a matrix or an operator. And that is what this notion is. And this notion says that if I were to go back to Dirac notation and write this, it says that the expectation value of an operator A is just a trace of an operator. If I go backward in my notation, times the outer product between the two state vectors. Okay, this is just the outer product, and then this can be written as A hat times rho hat. This is not in Hilbert space notation now, because this is just an operator which is in an infinite dimensional space. And so the expectation value of an operator is just a trace of A times its density operator. And this is called a density operator or density matrix. And this is called a density operator. Okay, so these are fairly important concepts in quantum mechanics. The concept of a density operator. It's good in the sense that phase is not necessary, or absolute phase is not necessary in quantum mechanics. If I use a state vector approach, the phase of these functions are not important, because finally what matters is the inner product between vectors, like forming things like this to find expectation values. So the absolute phase is not important, but the relative phases is very important in quantum mechanics. And when you form something like this, you take conjugate transpose and multiply. You only have relative phases in this kind of quantity. You don't have absolute phases. Absolute phases cancel out. So the density matrix representation cancels out all the absolute phases. Only relative phases are important in this kind of manner, to define the state of a quantum system. Let's take a 5 minute break and come back and talk more. Okay?